All right, so today we're going to be talking about how angular momentum and electron angular momentum can interact. And not surprisingly, that means we're talking about magnetic fields. So what we're specifically looking at is how we can combine the vectors of orbital angular momentum and spin angular momentum to essentially interact with each other, because these will represent the magnetic fields that comes with moving electrons. So a good way to think about this is I have an electron which is spinning and can generate an uh, up or down angular momentum. And this is going to have some sort of interaction with the orbital angular momentum of the actual electron moving around the nuclei. And turns out the best way to describe this is going to be using vectors. So when we do this, what we have to watch out for is, like most things, vectors, these can add together constructively or deconstructively. So a good way to think about this is that I've got two cars driving down a road at 60 miles per hour. Turns out that they can either interact by going the same direction, at which point if they collide, they barely graze each other, as the speed of the collision is almost zero. However, they can also end up coming in at opposite directions. Somebody crosses a lane, and then the speed of collision is closer to about 120 miles an hour. And that's more or less what we're doing with our vector addition. So because of this, what we can have is the orbital angular momentum quantum number can have any number of values, depending on which orbit my electron is in. But this is where we get really lucky, because the spin angular momentum is always 1/2. So this means that we can be looking at our total angular momentum quantum number. Yes, we now have a new quantum number, as being equal to our orbital angular momentum quantum number plus or minus 1/2, as it's going to be affected by how it interacts with the spin. So this is actually fairly straightforward for a case like the 1s electron, because if I'm in an s orbital, L equals 0, and then all I'm left with is this plus or minus 1/2 term. However, due to the nature of how we define our orbital angular momentum as relating to a vector, we can't have any negative values. So turns out that if I have a s orbital, then my total angular momentum is going to be equal to the angular momentum from our spin. Nice and easy case there. Things get a little bit more messy, though, if I'm looking at a p orbital, because for a p orbital, L equals 1. So this means my total angular momentum can be equal to either 3/2 if my spins are lined up together, or 1/2 if they're pointed in opposite directions. So a good way to think about this is if you've ever gone on a teacup ride at a amusement park, where the teacups are spinning around some central point, but you can then spin the teacup. And I'll tell you, it makes a world of difference whether you try and spin in the same direction the ride is moving, or you try and fight the flow and spin it in the opposite direction. You're going to feel a big difference, as your effective angular momentum, or your effective how much you're rotating, and thus your NASA, is going to be a big difference between the two. And we're looking at a very similar thing here. But being P chemists, guess what we care about? We care about energy. So thankfully, the physicists have already generated equations for us to treat the energy of the interacting of two different magnetic objects, as they so often already do. So in this case, we're going to be treating our energy of interaction as the interaction between a magnetic moment, mu, which is essentially the magnetic field of the object we care about, in this case, the electron, and the magnetic field that it's moving around in, B. And so the total energy can be given as negative of mu dot product B, because guess what? These two are vectors, which means thus we have the dot product of two vectors. Always fun. But again, dot product is one of the simpler vector relationships that we can deal with, as it more or less is just multiplying all of the relevant component terms together and then adding them up. So we're going to treat this as simple multiplication for now. But unfortunately, we need to hijack this equation and slap in the terms we actually care about. And we can do this by saying that our magnetic field is going to be related to L, or the vector of our total orbital angular momentum. Note, we're now going to be talking about the vectors of the angular momentum, not the quantum numbers. We'll come back to them shortly. And because the object I actually care about is the electron, its magnetic moment is going to be proportional to the spin orbital angular momentum, S. And so the energy of interaction is going to be proportional to the dot product of our spin orbital angular moment, spin angular momentum, and our orbital angular momentum. Where one of the important take-home messages of this is going to be that if these two objects are parallel or pointed in the same direction, this means that our energies are going to be repulsive. And a good way to think about this is you're lining up two magnetic fields in the same direction. And as a elementary student who, any elementary student who loves playing with magnets can tell you, if you have two magnets pointed in the same direction, they don't like that. And this is going to be a repulsive force. However, if I make my magnetic moments pointed in opposite directions, then we have a nice little advantage, as opposite angular momentums are going to be attractive. So we're going to have a repulsive term dominating if I align my spins, and I'm going to have an attractive term if I oppose my magnetic moments. So let's go ahead and take a little bit tighter look on what this dot product term actually looks like. So we need to try and figure out how we can get some insight into solving the dot product of our orbital and our orbital and our spin angular momentums. And it turns out we can really get this by bringing in J squared, where J is our total angular momentum, which we know is just simply going to be equal to the orbital plus the spin angular momentum terms. So the total angular momentum squared is simply going to be the square of the sum of orbital and spin angular momentums. And this means that we can then FOIL it out. So our total angular momentum squared is going to be equal to our orbital angular momentum squared plus our spin angular momentum squared plus the dot product of our two angular momentums. Well, this is the term that we were looking for, and we already have some insight as to what these other three terms look like. So guess what we do? We go ahead and rearrange everybody and isolate our dot product term so that we can solve for our energies. And when we do this, we get our dot product is equal to 1/2 the difference in between the squares of our total and our orbital and spin angular momentums added together. So in practice, this is going to be our total squared minus our orbital squared minus our spin squared. Now, remember when I told you that these are going to be our angular momentum vectors or values? Well, it turns out way back when I gave you an equation of how we could convert in between our angular momentums and their quantum numbers. And it turns out that equation was the square of our angular momentum is equal to h bar squared times our quantum number times our quantum number plus 1. So we go ahead and insert that in for our total angular momentum, our orbital angular momentum, and our spin angular momentum. And now I have, as usual, a very messy equation. But we can go ahead and pull out our h bar squared out front. And then what we have is that our dot product of our orbital and spin angular momentums is going to be equal to 1/2 h bar. The difference in between our orbital angular momentum, or total angular momentum, times the total angular momentum plus 1, minus the same terms for our orbital and our spin angular momentum. So we've got a lot going on here, but this is actually relatively nice because we can take this equation and substitute it straight into our energy equation. And when we do this, we can start getting some nice take-home messages. First of all, if I want to try and minimize my energy, make it as low as possible, what I'm going to want to do is try and minimize my total angular momentum values. So I'm going to want to have each electron generating as little total angular momentum as possible, or as little magnetic field as possible, while simultaneously trying to have as large of orbital and spin angular momentum as possible. Or another way of looking at this, especially since I can't really change my S value for a single electron, is I want to try and use my spin to cancel out as much of my orbital angular momentum as possible, so that these negative terms will drive my equation and give me a very low energy. So this again just gives me a rough idea of what my energies look like. But you'll notice I have a proportionality. We hate proportionalities. So what we're going to do is go ahead and substitute this guy in to make an equality. So I can figure out the energy of my total spin orbit coupling, which we are going to denote as E with our 3 values: total, orbital, and spin angular momentums. And what we're going to do is more or less switch out our h bar squared for hc a tilde, where a here is going to be our spin orbit coupling constant. Yes, more long names. And this guy is more or less going to be an empirically derived value, though it is worth noting that with a lot more quantum mechanics, you can get a numerical value. But for our purposes, what's worth noting is that it's going to give us an energy in wave numbers, which we can then convert to joules with a factor of hc. And the other thing that we really care about is how it scales with atomic properties. So our spin orbit coupling is going to increase as a factor of the nuclear charge to the 4th power, and it's going to be inversely related to the electron shell, or the principal quantum number, as n to the 3rd. So in practice, this is going to mean that our spin orbit coupling is going to be very dependent upon both the identity of the atom and exactly what electron shell is being occupied. And a good way to think about this is that one of the reasons why we see terms that are related to the charge and the principal quantum mechanical number is that, go figure, both of these are related in determining electron radii. And the closer in an electron is to the nucleus, essentially the faster it's going to spin around the nuclei, and thus the greater magnetic field it's going to generate, and the larger the spin orbit coupling energy is going to be, whether it's positive or negative. But again, this is what's really going to be driving this coupling constant. Though for our purposes, this is something we're usually going to be trying to determine directly from spectra or will have already been provided. But there's another good take-home message for this. And that's going to be that in general, we're going to be looking at states with lower total angular momentum, where I've canceled out as much of my angular momentum or magnetic field with my opposing spin as possible, are going to be the ones that are the most favorable in energy. Because a good way of thinking about this is that uh, my orbital angular momentum and my spin angular momentum, their magnetic fields are going to be attractive to each other and will help stabilize the system. Now, equations alone only help so much, so let's try and apply this to some real cases. So one of the simplest cases I can look at is going to be an alkali metal, where I only have a single valence electron. So I only have to think about one electron at a time. So this will be any alkali metal, well, plus hydrogen. And in this case, my quantum numbers are going to be an arbitrary value of n. In the ground state, I will occupy an s orbital, so my L will be equal to 0. Spin will, as always, be 1/2. And this means that my total angular momentum, or J, will be 1/2, as negative 1/2 isn't possible. Or again, thinking about this, J is equal to L plus S. So of course I'm going to have a total angular momentum of 1/2. And then when I plug this into my energy equation, where again I denote my total, orbital, and spin angular momentums, I'm going to have my nice little constant of 1/2 hc times the coupling constant times 3/4 minus 0 for my orbit minus 3/4 for my spin. So what we're going to find in this case is, notice, my total angular momentum and my spin angular momentum terms completely cancel out. So go figure. My spin orbit coupling energy for an s orbital is going to be 0 because I have no orbital angular momentum for my spin to couple with. Another way of thinking about this is, while I have a magnetic moment, I have no magnetic field for it to interact with. So there will be no interaction energy. And this is actually a fairly useful trick that is used quite often in spectroscopy, that you don't have to worry about spin orbit coupling for states for s orbitals. However, let's go ahead and again think about my alkali metal, and let's say I want to excite this electron. Well, if I do that, my n will increase, my L will increase by 1, my spin won't change, and well, some interesting things start happening to my total angular momentum. So in this case, n will increase, my L is 1, and as a consequence, my total angular momentum can now either be 3/2 if my spin and orbit couple together, or 1/2 if they end up being opposed. So this is going to give me two possible energies. The first of which is going to be for our J equals 3/2 state. And so in this case, we have our 1/2 hc times this spin orbit coupling constant times 15/4 minus 2 for the orbit minus my 3/4 for the spin. And when we put this all together, what we end up with is an energy of 1/2 times hc times the coupling constant. So a good take-home message of this is going to be to focus on the sign. It's positive. That means that I destabilized my electron, as the energy is going to be slightly higher than it would be if I had no spin orbit coupling at all, by again about 1/2 hc times the coupling constant. So this only gives me so much information. I want to figure out exactly how this energy compares to my other possible state. That way I can see which one's more favorable. So if I plug in a value of for the uh, total over uh, total angular momentum of 1/2, then what we end up with is 1/2 hc times the coupling constant of 3/4 for the total minus 2 for the orbital minus 3/4 for the spin. And again, my spin and my total cancel out. I get a minus 2, cancels out with the half. And congratulations, we have a minus hc times the coupling constant. So the real important thing to notice here is this is a negative value. So this means with my lower total spin or total angular momentum, I have stabilized this arrangement. And so this configuration is going to be uh, more favorable than we would expect if there was no spin-orbit coupling. So again, we have an attractive term in between my magnetic field generated by the orbital angular momentum and the spin angular momentum. So this also means that if I compare these two, that my two states are going to be will differ by about 3/4 of hc times the coupling constant. And this is going to be true for any set of alkali metal excited states, because I'm always going from an s orbital to a p orbital. So we're no spin orbit coupling to this 3/2 difference. And it turns out that for sodium, this has a value of 17 inverse centimeters, or about 3.4 times 10 to the negative 22 joules. Or if we compare this to the energy of the actual excitation itself, of about 17,000, it means that my spin orbit coupling energy is about 0.1% of the excitation energy. So yes, we've been spending this entire time talking about something that makes a very small difference to the relative energies of an electron configuration. So this is what we call a fine-tuning correction. But it will play a significant role in predicting which arrangement will be the most favorable in given ground states. And it's also been fairly useful as, again, this fine correction for spectroscopy. And thus, we tend to call this guy spin-orbit coupling as providing the fine structure to an absorption spectra. So if you have an absorption spectra, instead of a single peak when you look at sodium, if you look really close, you'll notice that that peak is going to be split into two. One for the J equals 1/2 state, and one for the J equals 3/2 state. But one of the last things I want to kind of leave you with is this idea of how I can, first of all, determine my spin orbit coupling constants and what sort of relative magnitudes I expect for these values. So what I can do is rearrange my equation for the change of energy equaling this 3/2 hc alpha, and then rewrite this as the spin orbit coupling constant is equal to 2 times the difference in energies over 3/2 hc. Now, in this case, I get really lucky because my energies were already in wave numbers, so I can ignore this hc term. And it turns out that for sodium, my coupling constant is somewhere around 11 inverse centimeters. And it's not unsurprising to see coupling constants sitting in this kind of 1 to 100 range, which again, being very dependent upon the size of the atom and exactly what orbit is being filled. So this should kind of give us a rough idea of how my spin angular momentum and my orbital angular momentum can interact. So we're going to try and develop this idea a little bit more and try and find an easier way to talk about electron configurations as I go to multi-electron systems next time. Thanks for bearing with me. Try and stay healthy and take care, everybody.